Geometry? Hell yeah. Chemistry? Hell yeah. Chemical geometry?
Hell yeah.
Chemistry has a lot of weird shapes. Like, some guy in Australia is trying to make a cube in his crack shed. Yeah, right. Anyhow, I found a shape that deserves all the attention. 111 propellane. Like, they use it in molecules to make it not planar, and then it can have some more 3D shape. For medicine and stuff. And maybe it can work better. Amazing. I guess it's the same for cubane, but this one is so strained, you can open her up real good. So let's just propel ourselves into the synthesis. So I set up a 3-neck flask with a stir bar in a heating mantle and add 72 ml of pyridine. I then add a funnel and 41.7 grams of Pentaerythritol. I remove the funnel and attach a thermometer to track the internal temperature. Then I attach a condenser and a dropping funnel. And to the dropping funnel, I add 73 ml of thionyl chloride. I start heating the flask to about 65 C and gradually add the thionyl chloride to the flask. I continue the addition slowly while keeping the temperature between 65 and 95 C. When the addition is complete, it is a clear yellowish liquid. I then heat it to a reflux and leave it overnight. In the reaction, thionyl chloride will chlorinate the hydroxyl groups of pentaerythritol, where pyridine improves the reaction rate by facilitating proton transfer, and largely prevents the formation of gaseous hydrogen chloride. The two main products, the trichloro and tetrachloro variants, will come in a 2.8:1 ratio, since we do not add enough thionyl chloride to chlorinate it all to the tetrachlorinated variant. Thionyl chloride is quite a harsh reagent, and will still chlorinate a large portion 4 times. In more detail, a lone electron pair from the hydroxyl group attacks the sulfur of thionyl chloride, causing one pair of bond electrons to move onto the oxygen. In the resulting intermediate molecule, the double bond reforms and kicks off a chlorine atom. Then, pyridine can take up the remaining proton. In the following molecule, the chloride ion attacks the adjacent carbon, causing it to kick off sulfur dioxide, which bubbles out of the mixture, and at the same time kicks off the remaining chlorine, which is taken up by the pyridine to form pyridine hydrogen chloride. This process happens 2 or 3 times more, to form the two major final products. When I come back the next day, the mixture has become a dark amber color, and the reaction should be finished. I then take it off heat and add 200 ml of water to separate out the product. The product is the layer on the bottom, and I leave it to cool down to room temperature so that it solidifies. When it has solidified, I set it up for vacuum filtration and wet the paper filter with some water. I filter all of the liquid through and wash it with some water to get out all of the starting material and pyridine salts. The product seems to be very sticky, and it is sticking to the bottom of the flask. Only a very little bit made it onto the filter, but it's okay, and I will just use the flask with the product like this for the next step. So the solid contains a mixture of the tetrachloro and trichloro product in an approximate ratio of 1 to 2.8. But for the next reaction, it is only the trichloro product that is doing something, and the tetrachloro is unaffected. So I set the flask in a heating mantle and start heating it to 70 C. I attach a stopper and then a condenser and a dropping funnel. I melt off all of the solid from the sides of the flask with a heat gun. Then to the dropping funnel, I add 90 ml of 60% nitric acid. When it has come to temperature, I add it gradually to the flask and red-brown gas immediately starts evolving from the mixture. This reaction is a simple primary alcohol oxidation, where nitric acid can oxidize the alcohol group to a carboxylic acid in 2 steps. Besides being an acid, nitric acid is also an oxidizer, so it can first oxidize the alcohol group to an aldehyde, and then to a carboxylic acid. When the addition was complete, I remove the dropping funnel and replace it with a stopper. The flask is filled completely with nitrogen dioxide gas, and I leave it to stir overnight and increase the temperature to 80 C. When I come back the next day, some nitrogen dioxide still remains, but I can't be bothered to wait for it to disappear. So I remove it off heat and add 200 ml of water to precipitate the product. We also see some product has sublimed onto the stopper. But because it is still too hot, the product separated out as a liquid. Very boring. So I wait for it to cool down and solidify. When that happens, the product has become the desired white solid, and I can filter it out. So I set the well-behaved product up for vacuum filtration, and I filtered it all through with some extra water. And it all came out of the flask cleanly, unlike that shit from before. We have some nice white crystals on the filter, and I dump it all into a beaker. This is still a mixture, containing the tetrachloro from before and the new acid product. So I will have to separate them, which should be pretty easy. I tried to crush it a bit with this thing, but it doesn't really work, so never mind. I then add 250 ml of a 1 molar sodium hydroxide solution, which will react with the acid to form its sodium salt and make it water soluble. I leave it to stir for a while to make sure all of the acid has reacted and dissolved. Then, I set it up for vacuum filtration to filter out all of the tetrachloro, which hasn't dissolved. I don't have use for the tetrachloro, so I just throw it away and take the filtered with the dissolved product. I put it all into a beaker and wash the flask with some water. I then drop in a stir bar and start adding in a random amount of 37% hydrochloric acid to precipitate the free acid product. It immediately precipitates as a white solid, and I add a little bit more acid to make sure it has all reacted. Then to dissolve all of the acid, I add a bunch of DCM. I then move it all to a separatory funnel and take the lower DCM layer. I then extract the remaining water layer several times with some more DCM. I combined all of the DCM extracts in a beaker and add some anhydrous magnesium sulfate to absorb remaining water. The solution becomes transparent, and I then filter it all through some cotton to remove the magnesium sulfate. I wash the beaker and filter a few times with DCM to make sure it's all washed down. I remove the filter and add in a stir bar. I then set the filter up for short path vacuum distillation to remove all of the DCM. When it is done, a white-yellow solid is left behind, which should be mostly the acid product, 3-chloro-2,2-bis chloromethylpropanoic acid. I crush up the product with a spatula, and then immediately continue with the next reaction. I again attach a short path distillation apparatus, but now without a vacuum. The only thing that this reaction requires is heat, so I start heating it to 210 C, and the product starts to melt. I insulate it with some aluminum foil, and when it comes to temperature, we see vapors escaping from the apparatus. I hold a wet pH paper to it, and we see that the fumes are acidic, which confirms that it is hydrochloric acid. Shortly thereafter, the liquid product starts distilling over, and I let it continue until no more product comes over. In the reaction, through heat, the product is getting decarboxylated and releases carbon dioxide, while hydrogen chloride is also eliminated. The heat causes the molecule to become unstable, where at once, the molecule kicks off carbon dioxide and hydrogen chloride to form a terminal double bond instead. This molecule has a lower boiling point, and therefore immediately distills over when it is formed. During the reaction, I put the receiving flask in a water bath to keep it cold and prevent losses. When it is finished, all that is left in the distilling flask is some good old black tar. In the receiving flask, I am left with 9.48 grams of a clear liquid, which is mostly the product 3-chloro-2-chloromethyl-1-propene. I calculated the yield to be 25% from the starting material, which is slightly lower than the literature, so it's not that bad. Now for the next reaction, I will have to form the dibromo carbene, which is done with Bromoform, so I add 37.15 grams of Bromoform to the previous product. Then as the two catalysts, I add 0.35 grams of pinacol and 0.254 grams of dibenzo 18-ground-6. I wait for it all to dissolve, and then to initiate the reaction, I add in 55 grams of a cold 50% sodium hydroxide solution. I then attach a condenser and let it stir for 1 hour at room temperature, and then at 40 C for 4 days. In the reaction, the double bond can react with the dibromo carbene to form the dibrominated cyclopropane product. The reaction is improved by addition of pinacol. Pinacol is a co-catalyst that improves the deprotonation in phase transfer catalysis, specifically for dihalocarbenes, while dibenzo 18-ground-6 acts as a phase transfer catalyst and also improves the workup. In more detail, the hydroxide ion from sodium hydroxide forms water by deprotonation of bromoform. A bromine atom is then kicked off and forms sodium bromide with the remaining sodium ion. This results in the formation of the dibromo carbene, which has a lone electron pair on the carbon, which makes it very reactive. Carbenes react easily with alkenes to form cyclopropanes, and so the alkene of the reactant reacts with the dibromo carbene, forming the dibromo cyclopropane product. I checked back the next day and it has turned brown. I used a hot water bath to continue on, and after 4 days it has turned slightly darker and the reaction should be finished. I take it out of the water bath and remove the condenser. I then dilute it with 50 ml of water. I then set it up for vacuum filtration. I wet the filter paper with water and add a layer of sea light on top. I wet the sea light with water and then filter all of the mixture through. I wash it with some more water, and when it has all filtered through, I discard the filtrate and then scrape off the top layer of sea light that contains the brown residue. and put it all into a flask. To this, I add 50 ml of a 1:1 mixture of pentane and acetone. I then leave the mixture to stir for a few hours, so that all of the product can dissolve. When that is done, I filter it all through a glass frit, and mix it with some more sea light, which will hold on to the tar. I then pour all of the filtered into a beaker, and we see there is a brown layer on the bottom, which is just some tar dissolved in water. So to absorb it all, I add a bunch of anhydrous sodium sulfate. I then filter it all through some cotton into a flask, and set the filtered up for short bath vacuum distillation. I first remove all of the pentane and acetone, and then swap the receiving flask. I start pulling a strong vacuum and increase heat to start distilling over the product. I insulate it with a bit of aluminum foil and assist the distillation with a heat gun. After a while, the product starts coming over and solidifies in the condenser as a white solid. I stop the water flow through the condenser so that the solid becomes a liquid again, and then collect it all in the receiving flask. Afterward, I am left with a solid product, but also a liquid impurity. So I remove the impurity through gravity filtration. I then recrystallize the product by dissolving it in some boiling pentane. I boil the pentane with a heat gun, and when it has all dissolved, I set it in the freezer at -20°C. It has all crystallized out, but also trapped the pentane, so I filter it through a paper filter with vacuum filtration and wash it with a little bit of cold pentane. I leave it to dry on the filter for a while, so that all of the pentane evaporates. I then put it all into a crystallizing dish, and the yield turned out to be 6.62 grams, which is 29%. It is a lot lower than literature, but at least it is enough to continue. The smell of 1,1-dibromo 2,2-bis chloromethylcyclopropane is very artificial, sweet, and aromatic, but it is so strong it becomes nauseating from up close. From far away, the smell is quite pleasant. Anyhow, now I will use all of it in the final step to make 1,1,1 propellane. So I set up a small 3-neck flask with a stir bore and put it in an isopropanol bath with a thermometer. I attach a gas adapter and a funnel, and then put in all of the product from before. I then start cooling down the bath by adding in dry ice. After a while, it has cooled down to about -70°C, and I closed off the remaining necks with septa. I also attached a nitrogen line, with a needle serving as the exit. Then under nitrogen flow, I add 7 ml of pentane as a diluent. Now the only reagent that is needed for this reaction is methyllithium. It comes as a 1.6 molar solution in ether, which I have to take up with a needle and syringe, because it is pyrophoric, and therefore only comes with a septum cap. So over the course of about 15 minutes, I inject 37 ml of the methyllithium solution into the flask. When that is done, I leave it to stir in the bath for about 15 minutes. Then I take it out and set it in an ice bath for an hour. In the reaction, the reactant undergoes a double transmetalation with methyllithium to form 1,1,1 propellane. In more detail, methyllithium first attacks one of the bromines, forming an 8 complex. The carbon-bromine bond electrons then take up the lithium and kick off methyl bromide. The carbon-lithium bond electrons attack the carbon adjacent to one of the chlorines and kicks off the chlorine to form lithium chloride and the intermediate product. This then undergoes the exact same set of reactions to form the final product 1,1,1 propellane. When it is done, I set it up for short bath vacuum distillation and heat the water bath to 40°C. I also put the dry ice isopropanol bath from before under the receiving flask to prevent losses from evaporation. When it has come to temperature, a liquid starts distilling over, which should be a mixture of mostly diethyl ether and propellane and a tiny bit of pentane. When it stops coming over, only a yellow sludge is left in the distilling flask, which are mostly lithium salts. I transferred all of the distillate to a storage flask, and it should contain some 1,1,1 propellane. So to test if there's truly propellane in here, I set up a small flask with a stir bar, and add in 20 ml of the propellane solution. Then, I add 1.39 grams of thiophenol to the flask, which is in excess, to make sure all the propellane reacts. I then leave it to stir for 15 minutes at room temperature, while it is standing in normal room light. In the reaction, 1,1,1 propellane reacts quantitatively with thiophenol to form bicyclo-1,1,1-pentylphenyl sulfide. We can then isolate and weigh the product and see how much propellane was in the tested solution. In more detail, this reaction involves a radical mechanism that is catalyzed by small amounts of disulfide that are present in the thiophenol. The disulfide undergoes cleavage from visible light and forms 2 thiophenyl radicals. This radical can attack the bridging bond of propellane, after which the intermediate radical takes up a hydrogen from thiophenol, which produces bicyclo-1,1,1-pentylphenyl sulfide and regenerates the thiophenyl radical and can continue to react with more propellane. until all of the propellane is consumed. When it is done, I distill off all of the ether, and then dilute the residue with some pentane. I then wash it with a 1 molar sodium hydroxide solution, which will react with all the unreacted thiophenol to form sodium thiophenolate. I move it all to a small separatory funnel and mix it around. I remove the water layer and wash the pentane layer once more with some 1 molar sodium hydroxide solution. I then take the pentane layer and add some anhydrous magnesium sulfate to absorb any remaining water. I then set up a pre-weighed flask in a heating mantle with a funnel that is plugged with some cotton, and I filter the dried pentane layer through. I then wash the beaker and filter with a bunch more pentane to wash everything out and down. Now I set this filter up for short path vacuum distillation and remove all of the pentane. When that is done, a light pink liquid is left behind, which is bicyclo-111 pentylphenyl sulfide. I remove the stir bar, and the weight of the product turned out to be 1.09 grams, which is this amount of moles. So the same amount of propellane was in the 20 ml of solution. If we then calculate it to the total of 50 ml of solution that I had, that means that in the 50 ml there was 1.022 grams of 111 propellane, which is a yield of 69%. This is similar to the literature, where they achieved a yield between 75 and 88%. So it looks like we made some 111 propellane, although it seems that it only comes as a solution in diethyl ether in literature. So I guess I can't separate it. Anyhow, now I can finally propel myself out of here. Bye.